Okay, team, welcome. We're going to try a new thing today. This is a review of the computational component of the course. So how to calculate your R values and how to calculate your dew point. I've got a few meetings today, so I'm going to break this up. We'll do about a half an hour, take a break, come back and finish it up. Of course, so this is going to be multiple videos for you guys, but it'll be more or less a continuous stream. I've got a brand new setup to do this. So I don't know how it's going to work, but I'm optimistic. I think it'll be all right. So I'm going to present my screen. So you're looking at my Bluebeam screen right now. I've got this very fancy set with a touch screen so that I can do calculations for you. I did get feedback that it's very difficult to follow calculations that are already done in a spreadsheet or in a PowerPoint. So this is real time. This is a real world problem. I'm going to zoom in here. Hopefully you guys are able to. Yep, you are. Okay. We're working with a company called Horizon Legacy Construction who do 3D printed walls. And we are helping them develop a 3D printed wall assembly. I'm going to fill in here what is insulation. So the 3D printed wall assembly consists of a structural layer, which is the upper layer, a non-structural veneer layer. This is an exterior wall condition, which is the lower one, tied together and cavity filled with insulation. So here is the cavity fill insulation that I'm just highlighting in yellow. And so what we're going to do is we're going to calculate the effective R value of this assembly with all of the insulation in it. I introduced you to the isothermal planes concept when we were talking about this in class. Isothermal planes means that within any given plane throughout the thickness of the wall, the temperature is constant. And so the way we evaluate the performance of a wall, the R value of a wall, is we look at each plane, we slice each different plane, we calculate the effective R value of that plane, and then we add them all up, and that gives us the effective R value of our system. Remember that when planes are in series, we add the R value. When planes are parallel to the direction of flow, we add the U value, we add the conductivity. So this is the direction of flow into the page. When planes are parallel or in series, we add up the resistance. When planes are parallel to the, or sections are parallel to the direction of flow, we add up the conductivity. So here's a real world example. The first thing we did is we divided it into all the different layers. There's the inside. I'm hoping, yeah, you guys can see my terrific. You can see my cursor. We have our inside air film. We have our first printed 3D printed layer. The red that you're seeing here is block lock reinforcement. So block lock. You know what I can do? This will be fun. Now you can see here, I can actually Google it. This is block lock. It's a ladder tie. This one has diagonal webs. This one has multiple interior webs. The very, very standard block lock would look like this. Maybe we can, no, that's got the diagonals. Anyway, you can have diagonal webs. You can have parallel webs. There's lots of different configurations of block lock, but it consists of wires that are welded together that get laid into the mortar joints of block. But we also use them to reinforce 3D printed walls. So what you're seeing in red is my block lock arrangement. So we're putting block lock reinforcement in to reinforce the wall. So our printed layer consists of the first layer, which is just concrete. There's a little skinny layer right through the wire, which performs differently because the wire is more conductive. There's a layer inside the wire, or inside relative to the wall, which is concrete that has the perpendicular wires going through it. Then we have a layer through the through this portion where it's back printed to create this core. Little sidebar here. The structure has to consist, the 40 millimeters of 3D printed concrete has no effective structural capacity. It's much too slender. So what we need to do is we need to introduce a core. The core has a hollow part in it that allows us to put reinforcing in if we need it. So we back print here parallel to the outside or the inside face. And so that's a layer. Then there's the layer through the center of the core. Then there's the layer through the inside face shell. Then there is there's the thermal break layer. We've said that it's 25 millimeters thick, where there's no concrete crossing. And then we've got 3 layers of our exterior shell, and then we have our exterior air film. So we have 12 different layers. So this is going to give us lots of practice calculating this one. So zoom back out here. Let me see if I can actually use this tool the way it's supposed to be used. Pen setting. I'm going to go, oh, damn it all. Bear with me. I've got to calibrate my darn working area. Center red dot. Okay, let's try this now. Layer 1, interior air film. Okay, how do we get the R value of the interior air film? Sorry, that's just a squiggle. Well, we look it up. So I happen to have lined up here a spreadsheet, which I'm putting in the download section, so you've got access to it. This stuff has been in your notes. Where this comes from, actually, I'll share. Oh, Jesus. You may remember that I shared this document and a link in our I shared this document and I shared a link to the website that contains this document. This is published by Natural Resources Canada, and it is just tables and tables and tables of R values for various materials. Rather than having to navigate through that, I consolidated this into a spreadsheet, which I've shared. So here's our spreadsheet, categorized everything here. These are a list of categories and these are a list of tables. So we're going to come here and we're going to look at air films, interior walls. Here is our RSI value, and the quantity is each and the per each. So the interior air film has 0.1, has an R value of 0.12. So I'm for the purpose of escape. Lead. Okay, R 0.12 for interior wall. So and this is the RSI. We're going to come back here and look at the defined units. Back to the source. Here's our defined units. Meter squared, Kelvin per watt. Remember that watt is joules per second. So it's the rate of heat transfer. Meter squared, Kelvin is the temperature difference. Meter squared is the face area. So the unit of RSI, meter squared Kelvin per watt. I'm going to come back here. And just, this is the only time I'll bother writing it on this, but it's important to just know what our units are. Meter squared, degree Kelvin per watt. Okay, that was easy. Layer 2. This is solid concrete. Thickness, the thickness T equals 40 minus 6 over 2. If we zoom in here, we would see that our bar thickness, this is our bar. We know that this is 40. This is 6, which makes this 17, and this 17. 17 millimeters. Our R. Okay, now we got to go look up our R. We're going to go back to our handy table. Structure, this is on my layer types. These are in order, so we see structures right down at the bottom. Go down here to structure. Structural materials, concrete, 0.0004 per millimeter. Equals 0.0004 per millimeter. 0.0004 times 17 millimeters equals 0.0068 meters squared degree Kelvin per watt. I should say, maybe I'll scratch this here. I'll write in the unit. This is 0004 meters squared degree Kelvin per watt per millimeter. So that's the one we looked up, is the R value per millimeter, and the R value of the overall layer is that. So for, just going to come back here because I don't want it to cause confusion. You can see that in my per column, my per can either be each. So the Schock isoCorb has an R value of 2.3173, irrespective of thickness, whereas concrete is an R value of 0.0004 per millimeter. So to get the R value of the layer, you need to multiply that by the thickness. Okay, we'll come back here. Layer 3. Now, I'm going to draw a little elevation of the wall, because here we're cutting right through the bars. This is an elevation section. And the bars are at 400 millimeters on center. So here's our elevation section. We're cutting right through the bar. Bar is 6 millimeters thick. We have 400 center to center. To the 600 millimeter wide. 600 millimeter wide elevation section. Okay. So the first thing we need to do is we need to figure out what is the R value of the various constituent layers. So we know that this thickness, here, I'm going to write it over here. Oops. The thickness of this layer is 6 millimeters, because the thickness, we're cutting right through the bar up here. So the thickness of it is 6 millimeters. So we're going to say that the concrete R equals 0.0004 times 6 millimeters equals 0.0024 meters squared degree Kelvin per watt. So that's the R value of the concrete within the layer. The rebar stainless R equals, now we're going to flip over to our spreadsheet again. Structural materials, stainless steel is the third one down, 49.88 times 10 to the minus 6. 39.88 times 10 to the minus 6 meters squared degree Kelvin per watt per millimeter. So R equals 49.88 times 10 to the minus 6 times 6 millimeters equals 0.00 0.00299 meters squared degree Kelvin per watt. U, the conductivity, equals 1 over R equals 1 over 49.88. Sorry. Oh boy, I wish I knew how to erase my marks. Oh yeah, not so bad. Okay, so let me just draw a line here. Say we're going to start into something new. U equals 1 over R. U is the conductivity, R is the resistance. So U equals 1 over R. So U for the concrete portion equals 1 over 0.0024. Is 416.67 watts per meter squared degree Kelvin. See, remember that R value is meter squared degree Kelvin per watt. U value is the inverse, watt per meter squared degree Kelvin. So that's the U of the concrete. U of the rebar equals 1 over 0.0000299 33 3344.5 watts per meter squared degree Kelvin. Okay, now remember we add up the U value because these are things that exist in a layer. So we're going to add up the U values, but we need to make them proportional to the area. So concrete, well, let's start with rebar. A rebar over A total. And so now I'm talking about the area projected on the surface. This is the areas we're talking about. So A rebar equals 6 times 400. Oh, sorry, 6 times 600. Six times 600 over 400 times 600. 6 is over here. That's the thickness of the rebar, 600 long. That's the area of the rebar when I cut through the vertical cut. Divided by 400 times 600, that's the area of the area that I'm considering. So why did I choose 600 by 400? I could have chosen anything, It happens that 400 is convenient because that's the spacing of my horizontal bars, or of my block lock is at 400. So 400 was convenient vertically, and 600 is the module. I'm just going to change this here. We'll change this to 600 just for convenience. It's not meaningful. 610 is 2 feet exactly. And so we're often converting back and forth between metric and imperial. So we would use a hard conversion. I'm using 600 for the sake of the problem because it's just a little more convenient. So the total area is 600 by 400. So 6 times 600, 6 times 600 divided by 400 times 600. I get 0.015 equals 1.5%. So 1.5% of that surface area is rebar. Concrete over A total equals 100% minus 1.5%. It's simply the rest. It's also equal to 394 times 600 over 400 times 600 equals 98.5%. And so the U value of the layer equals 1.5% times the U value of the rebar, 3344.5, plus 98.5% times the U value of the concrete, 416.7. Equals 460.6. 460.6 watts per meter square degree Kelvin. And that is for layer 3. The U value. So R layer 3 equals 1 over 460.6 equals 0.0022. So let's go back and compare that to layer 2. Our R value is 0.0068 when it's solid concrete. Layer 3, when we've got the rebar, it's 0.0022. The cold bridge is actually meaningful. Also the thickness, of course. So let's look at layer 4. This is concrete with wires. We're going to do the same thing. We're going to look at what this looks like in elevation section. We have 600 millimeters. It's the width. Hundred high. We have 3 of these. We've got our 3 wires crossing. They're 6 millimeters diameter. Okay, let's look at this. There's our crossing wire, 6 millimeters diameter. A of the wire equals pi d squared over 4. It's pi times 6 squared divided by 4. It's 28.3 millimeters squared. Okay, now the thickness of this layer is 17 millimeters. Now, when you get good at this, here, I'm going to go back and we're going to remind ourselves what layer we're talking about. We're talking about this layer here. That's layer 4. Right? And you can see we got a rebar. There's our bar coming through. So we've got these bars, these 3 bars coming through the 600 millimeter width. It's 17 millimeters thick. Now, once you get good at this, you'll realize you've already calculated some of these things. We're going to use this as a way of checking our work because I have not solved this problem before. We're doing this in real time. Okay, so the concrete. R equals, we got to look up our concrete again. So I'm going to flip back to here, and you can see that concrete 0.0004 per millimeter. R equals 0.0004 meters squared degree Kelvin per watt per millimeter times, how thick is this? 17 millimeters thick. Equals 0.0068 meters squared degree Kelvin per watt. Okay, here's where we're going to go back and check our work because we know that we already solved that one. Layer 2 are 0.0068 meters squared degree Kelvin per watt. So we did it right. Okay, because I know I'm going to need my U value, so I'm going to go U. Let's put the subscript here. 1 over R concrete. 1 over 0.0068. One 147.1 watts per meter squared degree Kelvin. So that's the concrete within this layer. Let's look at the rebar. R rebar. We're going to look it up again. Stainless steel, 49.88 times 10 to the minus 6. You see that right here. Oops. 49.88 times 10 to the minus 6 meters square degree Kelvin per watt per millimeter times 17 millimeters. Equals 0.00085 meters squared degree Kelvin per watt. Now we can't go back and check because we never calculated the rebar over this thickness before, but we know that it's about 3 times the thickness of layer 3. So let's have a look at layer 3. Layer 3 rebar R is 0.000299. 0.000299. Let's move times 17 divided by 6 gives us 0.00085. So all I did is I come back. I know I calculated rebar on a 6 millimeter before, just making sure that the proportion is correct, and it seems to be. I'm going to tell you that the safest thing we can do as structural engineers is always maintain a redundant process. Every single calculation we do in a redundant way. And if the two are the same, we're comfortable. If the two are not the same, we figure out where the mistake was. So U rebar equals 1 over R rebar equals 1 over 0.00085 equals 180.4 watts per meter square degree Kelvin. Now we need to know area of rebar over area total is 3 times 28.3. So that's the cross-sectional area of our bar is 28.3 divided by 400 times 600. Is 3 times 28.3 divided by 400 divided by 600 equals 0.00035. Three times 28.3 divided by 400 by 600. And then a concrete over a total equals 400 times 600 minus 3 times 28.3 over 400 times 600 equals 0.99965. So the U value of our layer equals 0.00035 times the U value of the rebar, 1180.4 plus 0.99965 times the U value of the concrete, 147.1. 0.00035 times equals 147.5. This is the U value of our layer, watts per meter square degree Kelvin. Okay, so we went from 147.1 to 147.5 as a result of these 3 bars going through. It's peanuts. We'll get to know when it's worth doing the calculation and when it's not. Here, it was not worth doing the calculation. But what's interesting is, remember I've told you that the better the insulator, the more important the cold bridges are. We're going to see that it actually does make a difference when we do the next layer. So the U of the layer, this is layer 4, 147.5. So R layer 4 equals 1 over 147.5. Zero point 0068 meters squared degree Kelvin per watt. Okay, those are our first 4 layers. We're going to take a break because I've got a meeting, and I'm going to come back and we're going to do the rest of the layers. Short meeting. So I'm going to once again share my screen. You'll recognize where we are. We just calculated the R value of layer 4. Switch pages. Actually, maybe we'll go back to the first page. So layer 4 is the layer just on the inside of the portion of the 3D printed wall closest to the core, to the center. We're moving on to layer 5. Layer 5, see how there's this back print here? So layer 5 goes through the back print. That's the one that we're concerned with. You know what I'm going to do is I'm going to copy this, grab it. We're going to put that on our fresh page so that we can have it to refer back to. So I come in here, layer 5. Layer 5. I'm going to call this the back print layer. Thickness of layer 5 is 40 millimeters. And you can see that within layer 5, we've got three elements. We have the rebar within a 600 millimeter width. We have 3 bars going through. We have 156 millimeters wide of 3D printed concrete. And then the remainder of the width is the insulation. So let's look at the various layers. Let's start with rebar because we always seems to be convenient if we do that. So rebar. R equals, we're going to flip over to our structural materials, stainless steel, 49.88 times 10 to the minus 6. R equals 49.88 times 10 to the minus 6. Remember that R equals meters squared degree Kelvin per watt per millimeter times the thickness of the layer, 40 millimeters. Equals 0.001952 equals 0.002. We're just not going to carry that many significant digits. Rebar, concrete. R equals, let's go back and look. Concrete, remember 0.0004. 4 meters squared degree Kelvin per watt per millimeter. Oops, that's millimeter times 40 millimeters. Equals 0.016 meters squared degree Kelvin per watt. And then there's the insulation. The insulation here is medium density urethane. So we'll flip and we'll look. R equals, we're going to come to our table. R equals insulation material spray applied medium density. So this isn't actually spray applied, it's a cavity fill, but it's a medium density urethane foam. It's the same as the spray applied stuff. Oh, look at this. You know it. There we are. 0.036 per millimeter. Per millimeter. Okay, so I'm going to flip back here. Look, you can see that my per is per millimeter. It's not per each, per millimeter. So it's 0.036 times the thickness. One point four four. 1.44 meters squared degree Kelvin per watt. Oh, I forgot to work out my U values at the same time. So I'll do that right here. So U rebar equals 1 over 0.002. It's 500. U concrete 1 over 0.016 equals 62.5. And then U insulation equals 1 over 1.44 equals 0.694. And remember that this is units are watts per meter squared degree Kelvin. Okay. Now I need to know, what are my percentage areas? So A rebar over A total equals 3 times 28.3 over 400 times 600. 3 times 20. Zero point zero 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 35. We're going to go back because this is a familiar calculation. We already know, we've already calculated what the area rebar is. And it's the same. One thing I didn't do on this one, let's draw an elevation of that layer. There's our square. Within that layer, we have insulation, we have concrete, and we have some bars running through. So we have 1, 2, 3 bars. I'm going to just hatch the insulation. Now I'll dot the concrete. So there's an elevation of a sectional elevation. This is 400. This is 600. And this, remember from the plan, is 156. Okay, area of concrete over A total is 400 times 156 minus 28.3 all over 400 times 600. Okay, so why do we minus the 28.3? Well, you can see that within that width of concrete, 1 bar goes through. So there's slightly less concrete. Let's see. 400 times 156 minus 28.3 divided by 400 by 600, 0.260. So 26% concrete. And then A insulation over A total equals 400 times 600 minus 156. So that's what's left of the width. The 600 minus 156 is the width of insulation, minus 2 times 28.3 all over 400 times 600. Sorry about that. It just kicked me out. Fortunately, unlike last week, I knew that it kicked me out when it did, and so I joined right back in. There. If you're on a phone, I simultaneously join on my phone. Sorry about this. I got a terrible echo. Okay, that might be better. Simultaneously join on my phone because otherwise it thinks there's nobody here. Okay, A insulation, we're A total is where we were. And it looks like I calculated 0.73976. And if we add that up, plus 0.26 plus 0.00035, that should equal 100%, and it does. Okay, so now our U value for the whole layer, for U value for layer 5 equals 0.00035 times my rebar U value, which is 500. Well, that's here. Plus the concrete, 0.26 times the U value for my concrete, which is 625. Plus 0.73976 times the U value for the insulation, which is 0.694. Get 18.5. This is 62.5. You can't see that. I'm going to do this calculation again because it's an easy one to get off track. So 0.00035 times 500 plus 0.26 times 62.5 plus 0.73976 times 0.694 equal, now I got 16.9. Now I got 16.9. Let me try that again. Third time. Sixteen point nine. I got. This is a redundant process. I got 16.9 twice out of 3 calculations. So now I'm comfortable that 16.9 is correct, and that is in watts per meter square degree Kelvin. So therefore, my R for layer 5, 1 over 16.9. 0.059 meters square degree Kelvin per watt. Okay, layer 6. I'm gonna pull this guy over with me because it's helpful to refer to. Layer 6 looks an awful lot like layer 5, except different proportions, right? So layer 6. Oh, and different thickness, of course. This is through the core. Thickness equals. Yeah, I'm gonna start being very disciplined about using my subscripts so that you learn it as a good habit. Okay. It slows me down, so I may not carry on, but I may not do it all the time. But look, T layer 6 equals 76 millimeters. Rebar. R equals. We're going to look it up again. Structural materials, stainless steel, 4988 times 10 to the minus 6. 49.88 times 10 to the minus 6 meters squared, degree Kelvin per watt per millimeter times 76 millimeters. Zero, 0.0038. Remember when I told you that the imperial units are just more convenient? When we work with metric units, this is too often the case. We're working with either extraordinarily small or extraordinarily large numbers, whereas imperial units, they're just easier to manage. Okay, 49.88 exponent 6 plus or minus times 76, and double check the calculation, 0.0038 meters squared, degree Kelvin per watt. So U rebar equals 1 over R rebar, 1 over 0.0038 equals 263.8 watts per meter squared, degree Kelvin. 1 divided by 0.0038. 263. Okay. Subscript there. Then we're going to look at concrete. R concrete equals, I do these from memory now, 0.0004. 0.0004 meters squared, degree Kelvin per watt per millimeter times 76 millimeters. So 0.03. So then the U concrete, 1 over 0.0304 equals 32.9 per meter squared degree Kelvin. And then insulation. Flip back to our spreadsheet. We go up to the insulation products. We have the spray urethane form 0.036 per millimeter, 0.036 meters squared degree Kelvin per watt per millimeter times 76 millimeters. $2.736 meters squared degree Kelvin per watt. And the U of the insulation equals 1 over 2.736 equals 0.365 watts per meter squared degree Kelvin. Okay, now we've got within that layer all of our R values and U values. Now we need our areas. So in this case, through the core, we have two stripes that are 40 millimeters wide, and we have 3 bars running through, right? So that's hatched like concrete. That's our insulation. That's insulation through the core. As I say, we could choose any tributary area, but this is the convenient one. So we're looking at a 400 by 600. But because we're just looking at proportion of area, it doesn't matter what we take. We could take the whole wall if we wanted to. So we just decided to do this as one unit area. So we're going to do A rebar over A total equals 3 times 28.3 over 400 and 600. And 0.00035. Now, we've done this calculation a number of times now, right? With 3 wires going through it, and we got the same answer. So it's good to go back and check, because if we didn't have the same answer, we'd know we made a mistake somewhere. A concrete over A total equals 2. 2 times 40 times 400 minus 28.3 all over 400 times 600. Okay, so we've got these two 40 millimeter wide. Because this section is cutting through here, layer 6. So we have two 40 millimeter wide strips, 400 high, and the rebar cuts through one of them. I get 13.3, 0.1332. Let's just check that again. 2 times 40 times 400 minus 28.3 divided by 400 times 600. 13.3. And now let's look at the insulation. Equals 600 minus 2 times 40 times 400 minus 2 times 28.3. So we take the total area, we subtract the 2 vertical strips and the 2 bars that go through the insulation. All over 400 times 600 minus 2 times 40 times 400 minus 2 times 28.3 divided by 400 divided by 600. $0.131. That is not correct. Clearly, 600 minus 2 times 40 times 400 minus 2 times 28.3 divided by 400 and 600. Oh my God. So 600 times 400. It makes a difference. 600 times 400 is the total area minus the 2 concrete strips minus the 2 pieces of rebar divided by 400 divided by 600. 0.8664. Now, I never formalized this before, but we want to go back and check. Check. Area total over area total is 0.00035 plus 0.1332 plus 0.8664 all over 400 times 600. So you know what I should have done is I should have said, she used this symbol. Oops, not that symbol. Sigma A means that's the sum of all the areas. So let's see. 0.00035 plus 0.1332 plus 0.8664 equals divided by 400 divided by 600. Oh my God. I apologize for this. These are already percentages. So 0.00035 plus 0.1332 plus 0.8664 equals 0.99995. Okay. So it passed the check. So then we need to add up our U values proportional to our areas. So U layer 6 equals 0.00035 times the rebar, U rebar, which is 263.8. 263.8 plus 0.1332 times the concrete U value, 32.9, plus 0.8664 times the steel U value, the insulation U value, which is 0.365. What's that? U value. 0.00035, which is my percentage area of steel, times the U value of the steel, 263.8, plus 0.1332 times the U value of the concrete, which is 32.9, plus 0.8664, which is the percentage of insulation, times 0.365, which is the U value of the insulation. And I get 4.791. 4.791 watts per meter squared per degree Kelvin. And therefore, R value of layer 6 on over 4.791 0.209. Okay, I'm going to check this one more time because these calculations are easy to get wrong. 0.00035 times 263.8 plus 0.1332 times 32.9 plus 0.8664 times 0.365, 4.79. Invert that. Get an R value of 0.0209. There's layer 6. I am going to put a little box here. I'm going to say layer 7. Outer core shell. Okay, see, layer 7 is this one right here, outer core shell. You can see that it's identical to layer 5. I mean, we're forgetting the radiuses, so we're saying it's identical to layer 5, layer 7. I'm going to indicate here, identical to layer 5. 5. R layer 7 equals, back here, 0.059. Meters squared degree Kelvin per watt. And moving on to layer 8. So again, I'm going to copy this. So layer 8 is just the insulation. I'm going to call this the thermal break layer. It's the separation. Layer 8 is our thermal break. Thickness, 25 millimeters. T layer 8. T layer 8 equals 25 millimeters. Okay. Go to the elevation. Well, let's do it in the same order. Rebar. R equals, we're going back to our trusty spreadsheet. Rebar, stainless steel, 49.88 times 10 to the minus 6. 49.88 times 10 to the minus 6 meters square degree Kelvin per watt per millimeter times 25 millimeters. Equals 0.00125. And insulation. Insulation equals, back and look for our insulation value. Insulation spray applied, the top 1.036. We're still highlighting it. 0.036 meter square degree Kelvin per watt per millimeter times 25 millimeters. Equals 0.9. So if our R is 0.00125, let's work on our U values. U rebar equals 1 over 0.00125 equals 800 watts per meter square degree Kelvin. 1 divided by 0.00125, 800. For the insulation, U insulation equals 1 divided by 0.9 equals 1.11 watts per meter square degree Kelvin. Okay, we draw our elevation of this. .400 by 600 with 3 bars going through it. right? So we're going to say A rebar over A total. If we remember what this is, 3 times 28.3 over 400 times 600. Point 0035. A insulation over A total is 400 times 600 minus 3 times 28.3 all over 400 times 600. Something looks suspicious. I thought I was missing a 0. .99965. So there's our areas. So we know that our U for layer 8 equals 0.00035 times the U of the rebar times 800 plus 0.99965 times 1.11. $1.39. 1.39 watts per meter squared per degree. It's degree Kelvin. Let's try this again. 0.00035 times 800 plus 0.99965 times 1.11 is 1.39. R, layer 8, 1 over 1.39 0.720 meters squared degree Kelvin per watt. Okay, remember when I said that the impact of the cold bridge on the concrete is peanuts? And it was, because the concrete allows the insulator. Exactly the same cold bridge passing through, that is 3 wires, passing through the insulation reduces the R value of the insulation from 1.11 to 0.72, even though it is such a tiny, tiny area. It's like 0.03% or something. It's a tiny area, but steel is so much more conductive that the impact of the cold bridge is actually meaningful. Okay. R layer 9 equals R, which one is it? Layer 9 is identical to layer 4. 4. So we'll go back a couple of pages. Layer 4, R of layer 4, 0.000, or sorry, 0.0068. Oops. 0.0068 meters square degree Kelvin per watt. Our layer 10 equals our layer 3. See, layer 10 is right through the bar, same as layer 3. We're going to go back and find layer 3. Layer 3 are 0.0022. Our layer 11 equals our layer 2. You see, it's just the plain concrete. Layer 2 and layer 11, they're identical. Layer 2, solid concrete, are 0.0068. Oops. 0.0068 meters square degree Kelvin per watt. Okay, look at this. Our layer 9 and our layer 11 are the same, but they're not the same, right? Our layer 9 has a cold bridge, whereas our layer, whereas layer 11 doesn't. It doesn't have the wires going through it. In the concrete, because the concrete's a poor insulator, that cold bridge is a rounding error. In the insulation, it's not. It's meaningful. But in the concrete, it's a rounding error. They turn out, even though we did the calculation separately, they turn out to be the same answer. And then layer 12. Outer air film. Our layer 12 equals, and we're going to go back to our table of R values. We'll come up here. Air films, exterior, floors and walls, winter. Exterior ceilings, floors and walls, winter. 0.03. This is interesting. Exterior ceilings, floors and walls. The ceiling is interior, but I guess they mean roof. Okay, so exterior walls, 0.03. 0.03 meters squared degree Kelvin per watt. Okay. See if I still got that on my clipboard. I do. So here's our various layers. Oops. R layer 1. Zero 0.12. 0.12 R. This is meters squared degree Kelvin per watt. 2. Layer 2. 0.0068. 0.0068. We'll just infer units. Layer 3, 0.0022. Layer 4, remember we just talked about how layer 4 and layer 2 are identical. The difference is a rounding error. Five. R layer 5.059. Layer 6.209. Layer 7. Remember, layer 7 is identical to layer 5. Layer 8. This is going to be the good one. Layer 8 is our thermal break. Layer 8.720. 0.720. Layer 9. Remember, 2, 4, 9, and 11 are all the same. 0.068. R layer 10. Layer 10 is the same as layer 3. 0.0022. R layer 11. 0.0068 is the same as 9. R layer 12. Oops. Layer 12.03. That's our outer air film. And now we've calculated the R value for all our layers, and now we're going to add them up. Drop a pair. Here I count. Okay. So 0.12 plus 0.0068 plus 0.0022 plus 0.0068 plus 0.059 plus 0.209 plus 0.059 plus 0.72 plus 0.0068 plus 22 plus 68 plus 0.03 equals 1.229. 1.229 meters square degree Kelvin per watt. Okay, here's something I want to. I mean, these numbers are not. They don't appear all that meaningful, but let's do a comparison. To 181 millimeters of insulation. So this dimension here is 181 millimeters, right? 261 minus 80. So if we had the full benefit of all that insulation, 181 millimeters of insulation, R equals, come back here, insulation. Oops, we're going to slide down. Spray insulation, remember, 0.036. 0.036 meters square degree Kelvin per watt per millimeter times 181 millimeters. 6.516 meters square degree Kelvin per watt. The difference between the two, delta R, equals 6.516 minus 1.229 equals 5.287. 5.287 divided by 6.516 equals 0.81. 81%. The impact of these cores and the rebar as cold bridges reduces the effective insulation of our system by 81%. It's staggering. Cold bridges are really, really important. Far more important than they look, because you would look at this graphically, you'd say, oh, that looks like a pretty good wall system. And I said this to my client. I said, I think you're going to do pretty well with this wall system. Didn't realize the tremendous reduction. Okay, so there we've calculated our R values. I'm going to take another break, and then we're going to come back and we're going to work out where our dew point is within this wall. So I will see you shortly. Okay, well, welcome back, everyone. I don't know. Again. Okay, we're better now. So this is the final exercise we're going to go through. We're going to go through an exercise of how to calculate the dew point within the wall. So these are our two major calculations we do in this course are calculating your R value and calculating your dew point. So I'm going to walk through here carefully, step by step. The one thing I'm going to remind you is that the temperature change is the rate of temperature change is inversely proportional, is proportional to the R value. So the over the width with the highest insulation is the highest temperature difference. If you have very little insulation, there is almost no temperature difference from one side to the other, which completely makes sense, but the diagram looks funny. Because your mind thinks it's heat flow. But anyway, regardless, your temperature change is proportional to your R value within any given layer. And so what our task is to figure out what are the R values of the different layers and apportion the temperature change within those to those layers proportional to their R value. Okay, so having said that, let's give it a try. To simplify the problem, I'm going to combine the three concrete layers into one in each of the for each of the shells. So we're going to say R 2 to 4 equals 0.0068 plus 0.0022 plus 0.0068 equals 0.0158. 0.0158. And then our 9 through 11 equals the same, 0.0158. 0.0158. Okay. Now, the next thing to do is let's define our design condition. So indoor temperature and humidity, we're going to say T indoor equals 24 degrees Celsius and H equals 50%. This is our indoor design case. T outdoor equals minus 20 degrees Celsius. So that's our design case for Toronto. So delta T, which is the difference in temperature, equals 24 degrees Celsius minus 20 degrees Celsius. Oh my God, that's percentage sign. Sorry. Minus 20 degrees Celsius equals 44 degrees Celsius. Is the temperature difference between inside and outside. We're going to look at our layers. I'm going to re-summarize them here. R1 over R tote is 0.12 over 1.229, right? 0.12 divided by 1.229. .10. Therefore, delta T1 equals 0.10 times 44 degrees Celsius equals 4.4 degrees Celsius. Our 2 to 4 over our total equals 0.0158 over 1.229. So there's our 2 to 4. Zero 1.3. Therefore, delta T 2 to 4 equals 0.013 times 44. 0.56 or 0.57 degrees Celsius. Our 5 over our total equals 0.059 over 1.229. .048. Delta T5 equals 0.48 times 44 equals 2.11.
R6 over R total. 0.209 over 1.229. 0.17. Delta T 6. 0.17 times 44 equals 7.48. R7 over R total equals 0.059 over 1.229, same as R5, 0.048. Delta T 7 equals 7.48. Oh, sorry. Darn it all. Same as 5. 5, 2.11. 8 over R total equals, remember, R8 is my thermal break layer. 0.720 over 1.229. 0.59. 0.586. Therefore, delta T 8 equals 0.586 times 44. R 9 to 11 over R total. Now remember, 9 to 11 and 2 to 4 are the same. 2 to 4, 0.013. So therefore, delta T 9 to 11 equals 0.57 degrees. And then R12, R total equals 0.03 over 1.229. 0.024. Delta T R12 7. There's our temperature difference across. Now we want to add these up. Make sure they add up to 44. 4.4 plus 0.57 plus 2.11 plus 7.48 plus 2.11 plus 5.8 plus 0.57 plus 1.07 equals sum of delta T equals 44.11 degrees Celsius. Okay. That's a rounding error. So now we know our temperature at each, or our temperature change through each layer. I'm going to just copy this to the next page. Have it to refer to. Got to add a few pages. Actually, sorry. You have to indulge me here for a second. Let's grab just at the very end of this thing. Expand it like this. And pop these up maybe down here for reference. Okay. And we're gonna, that's too small. Okay. So now we're going to look at what our actual temperatures are. So at the boundary between 0 and 1, I'm going to call this 0. So T 0, 1 at that boundary equals, oops, T 0, 1 equals 24 degrees Celsius. T 1, 2, the boundary between 1 and 2 equals 24 degrees Celsius minus delta T 1 equals 24 minus our delta T1, which is 4.4, equals 19.6 degrees Celsius. The 4, 5. So this boundary between 4 and 5 equals 19.6 minus delta T 2 to 4, 0.57. 19.03 degrees Celsius. T56 equals 19.03 minus delta T5 equals 19.03 minus delta T5, 2.11. $16.92 7 equals 16.92 minus delta T 6. 16.92 minus delta T 6, 7.48. T at the boundary between 7 and 8 equals T 6 7 minus delta T 7, 9.44 minus delta T 7, 2.11. 7.33. T 8 9 equals T 7 8 minus delta T 8 equals 7.33 minus delta T 8, 25.8. 18.47. Whoa. Minus 18.47. T 9 11 equals T 8 9 minus delta T. Oh, sorry, that's not T 9 11. That is T 11 12. 8 9 11 12. Yeah. T at the 11 12 boundary equals T 8 9 minus delta T 9 to 11. 18.47 minus delta T 9 11, 0.57. Time. And finally, a little more space. Finally, the 12 infinity. I'm going to call that's the 0 layer. This is the infinity layer outside. T12 infinity equals T 11 12 minus delta T 12. 8.9 minus 47 minus 0.57. This is minus 19.04. minus 1.07 equals minus 20.11 degrees Celsius. So we're out by 0.11 degrees Celsius because we have 10 round, we've rounded the number 10 times. So that's a rounding error. So it's fine. So now we know our temperature at each interface. I'm going to choose a color that we don't have represented in here. Let's see, we'll do this one in bright green. We'll make it quite thick. And we are going to try and estimate what our temperature profile looks like through here. So this is 24 degrees. We are dropping 4.4 degrees. So that's 4.4. This is maybe not the best. Then we're dropping next to nothing. So we got a reasonable temperature drop through the air. Next to nothing through the concrete. Then a little bit more through here. A little bit more through here. A little bit more through here. And then 8, delta T 8, 25 degrees. Way the heck down here. Then next to nothing, and then a bit. So we can do this to scale. And we're going to see that our temperature plot looks something like this. I'm not going to bother doing it to scale because I'm not working in a program that works that way. But this is our temperature gradient. Where we have 24 degrees Celsius, we have minus 20 degrees Celsius, and then various temperatures in between. Okay, so what does that actually tell us? Well, we know that our indoor condition is 24 degrees and a relative humidity of 50%. So I'm going to go back to red here. Zoom in. Here's our 24 degrees, relative humidity of 50%. So I'm going to draw that. 24. That's our indoor condition. (24 degrees Celsius). RH equals 50%. Our outdoor condition this is our relative humidity with our relative humidity sorry, lost my train of thought here because I'm not zooming properly. Okay, we have a constant moisture content. Outdoors, we know we're at minus 20. And we want to know what the dew point of that air is. So we're going to come back and we're going to draw a line. Constant moisture content. Horizontal line is our moisture content. Here is 100% relative humidity. That is the saturation point. So this is our represents our saturation temperature or our dew point. Come all the way down here. Down. Dew point or saturation temperature equals 13 degrees Celsius. So if we have 24 degrees and 50% relative humidity, we're going to get condensation at a relatively high temperature. I have to admit that this is intuitively higher than I expected, but that's where it is. So 13 degrees is our dew point or saturation point of our air. Move this out of the way. We have we're identifying that our dew point was 13 degrees Celsius. So let's look at where 13 degrees Celsius happens. 13 degrees Celsius happens. T78 is +7. Oh, T56 is 16.92. T67 is 9.44. So T56 in here is 16.92. T67 is 9.44. And it's going to happen in between there. Now I'm going to a more descriptive slice of this thing. Kind of superimpose one over the other. There we have it. Okay. So we have 16.92 at this boundary here. At 16.92 this boundary here. This is my boundary 5, 6. This is my boundary 6, 7. And we know our dew point happens in there somewhere. Okay, so we know that T at boundary 5, 6 equals 16.92. T at boundary 6, 7 equals 9.44. And then delta T at 6 equals 7.48 degrees. Delta T from the dew point to boundary 5, 6 equals 16.92 minus 13 degrees equals 3.92 degrees. So 3.92 degrees is the difference in temperature from the temperature at boundary 5, 6 to the dew point. Delta T dP to 5, 6 over delta T 6 equals 3.92 over 7.48. .52. That means that within this zone, between within zone 6 or within layer 6, the dew point is just about halfway in. That the temperature difference between the 5, 6 boundary and the dew point is 52% of the temperature difference between the 5, 6 boundary and the 6, 7 boundary. And then the location equals 0.52 times 76 millimeters. 76 millimeters is that distance. Which is 40 millimeters. 40 millimeters from the 5, 6 boundary. So let's check this. Delta T from the dew point to the 6, 7 boundary. Sorry, over delta T 6, 7. Trying to kid. delta T from the dew point to the 6-7 boundary equals 13 degrees Celsius minus the temperature at 6-7, 9.44. Equals 3.56 degrees Celsius. So from the dew point to the 6-7 boundary is 3.56. Delta T from between of the dew point to the 6-7 boundary over delta T in layer 6 equals 3.56 over 7.48. Five six divided by 7.48. 0.48. 48. Now the location equals 0.48 times 76 equals 36 millimeters from the 6-7 boundary. So we calculated it from the from the 5-6 boundary. We calculated 40 millimeters. We calculated from the 6-7 boundary. We calculated 36 millimeters, and so that's correct. We got the same dew point moving either way. Okay, that is it. That's all I'm going to do for review. I'm going to share this presentation or this PDF with you. I'm going to tidy up that diagram on the left. I can't draw it to scale because, but I can certainly draw it a lot better than it is right now. So I'll tidy up the diagram on the left and save it so that you guys can sort of follow the process. And I hope you all do really well in the exam. And I hope this was helpful. And I'm going to look forward to seeing you on Monday. Okay. Bye, team.